Welcome back. So in this brief lecture, I will sort of re-emphasize or slightly elaborate on something which I've mentioned in the previous lectures. It is about Carnot efficiency and electrochemical energy conversion. So to appreciate this, first we have to interpret certain things in molecular terms. Okay, so what's the typical energy conversion process? Okay, so if you go to a coal power plant, okay, or some power plant which is based on hydrocarbons, let's say, you typically run some exothermic reaction. Exothermic reaction. There's burn, okay, typically burn fuel to generate heat. So typically when that is generated, heat is generated, it is supplied most to generate steam. Steam at high temperature. Okay, so what exactly do we mean by temperature here is what I want to clarify. Temperature, we want to interpret based on equipartition theorem. Right, this is something which you heard from high school, but we'll internalize it better here. Okay, so what is that? For every excited degree of freedom, for example, in supposing you have a gas molecule, okay, it has 3 degrees of freedom. That is, it can store energy. What first we'll clarify: excitable degree of freedom. Okay, modes in which energy can be stored. Right? For example, if you have monatomic gas, okay, you have in a monoatomic gas, you have 3 translation degrees of freedom. Okay, it can store kinetic energy in X, Y, and Z direction. Okay, 3 translation degrees of freedom. Okay, if we have, let's say, a diatomic molecule, in addition to 3 translation, you have you have vibrational degrees of freedom, right? So it can store energy in vibration, as well as it can store energy in 2 rotational degrees of freedom. Okay, so in polyatomic molecules, things become more complex and so on. Okay, so the main thing I want to emphasize: these are the modes wherein each energy can be stored. Okay, so what does equipartition theorem tell you? That for each degree of freedom, has the energy stored in each degree of freedom is half kT, right? So when you are increasing, when you say the system is heated, the temperature is increased, and temperature goes towards increasing the energy stored in each degree of freedom. Okay, so in an equilibrium system, each degree of freedom is, that is the average energy stored in each degree of freedom is the same, right? Every degree of freedom is equilibrated with every other degree of freedom. So each degree of freedom contributes to half kT. Okay, so for example, in a monothermic gas, the total energy would be, the average total energy would be 3 by 2 kT, right? So that is what. Okay. So what happens? So typically, how does an energy? Whenever we are thinking about energy conversion, we are thinking about heat to work conversion. Right? So every work conversion involves movement of a piston. Movement of a piston or lifting a weight. Okay, so you can, or lifting a weight. Right? So any work can be interpreted in that manner. Okay. So typically, why is there a Carnot efficiency? Molecular reasons. Molecular reason behind Carnot efficiency is the following. Okay, this is the crucial argument. Yeah. So what is happening when you are converting? How is the energy conversion process occurring? Okay, so you have a steam coming from a hot reservoir, all right? So that is at a high temperature. That is the average kinetic energy is high. Okay, so this is like TH of a steam molecule, let's say water molecule coming in at a high temperature. Okay, so high kinetic energy. This means high kinetic energy. Okay, and then this goes. What does it do? So it hits a piston or a turbine blade. Okay, and then this moves. Okay, uh, gives rise to motion, okay, translation motion of the piston. Of the motion, and then the molecule is reflected back. Okay, so that is reflected back after giving off some kinetic energy. Okay, so what is important? So if you say something is hot, okay, so here this kinetic, the energy is stored in 3 degrees of freedom, right? Equally stored, energy equally stored in 3 degrees of freedom. Okay, but this is translation of a piston along one dimension, along in one direction, along a certain direction. That is work. Okay, this is the way we interpret work. This is heat. Okay, so it is never possible for energy that is stored in 3 degrees of freedom to be entirely converted to motion along 1 degree of freedom. Okay, so some energy is always left over, and after supplying some energy, okay, so this energy that is it collides. There is a momentum transfer to the piston. Okay, so this is piston wall. Okay, so this is piston wall. This indicates piston wall. And then this molecule is reflected back, okay, with reduced energy, okay, because some momentum has been transferred to the piston. Okay, so there are many momentum is much heavier. The piston wall is much heavier compared to a mass of a gas molecule. But you have to think that there are many such collisions which at a given instant of time to facilitate the movement of a piston wall. And then when it reflects back with a lesser energy. Okay, so that is lesser what energy? The energy stored in the translation degrees of freedom, but that is less. Okay, so that is indicated by TC, cold. Okay, this is the hot. This is indicative of energy of the hot reservoir. This is indicative of energy of a cold reservoir. Okay, so this leftover energy. Okay, so this is the reason. What is the reason for Carnot efficiency? It is never possible to convert energy stored in 3 kinetic energy degrees of freedom, okay, so vibration degrees and so on, okay, into one-dimensional motion for piston. Okay, so this is never possible. All right, so when it comes back, it is always there is some leftover energy. Okay, so leftover energy. Okay, so if you look at the formula of Carnot efficiency, this is the formula, right? So TC, this is never zero. Can never be zero. So this is the molecular basis for Carnot efficiency. For Carnot efficiency to be 100%, TC should be zero. Right? That is the average kinetic energy or the average temperature. The temperature of the outgoing molecule has to be zero, which is never possible. So which are the energy conversion systems, okay, which are limited by Carnot? Heat, whenever there is a thermal or a thermal energy to work, this is limited by Carnot. Okay. However, why we are very interested in fuel cells and battery is because we are here, we are thinking about what is this energy conversion? Okay, what's the fuel cell? First, for example, here you have again in the simplest fuel cell, you burn hydrogen. Okay, you convert hydrogen, you react hydrogen and oxygen electrochemical. Okay, it's not combustion. Okay, so even though we say burn, we are burning electrochemical. We'll see in a subsequent lecture. Even in a battery, there is some exothermic reaction. The lithium-ion battery, on one side, lithium getting oxidized and the other into lithium plus, and then it gets transferred to via an electrolyte and binds to, let's say, transition metal oxide. Okay, so there is an exothermic reaction, which gives rise to work. Okay, electrical work. So there is energy that is stored in chemical bond energy is converted to electrical work. So this is not limited by Carnot. So this is very, very important. So people are trying to, so that's why, see, if you go to an average thermal power plant, okay, the efficiency is about 30%. Okay, so efficiency of a thermal power plant is about 30 to 40%. Okay. However, if you have, let's say, a solid oxide fuel cell, it generates, let's say, hydrogen. It uses up hydrogen and oxygen to generate high temperature steam. And this steam that is generated in a solid oxide fuel cell the efficiency of solid oxide fuels. Okay, this operates at very high temperature. Okay, so the high temperature steam, if it's used for running a turbine, okay, the combined efficiency of such a system can be above 90%. Okay, so this is very, very highly efficient system. Okay, so first there are two aspects. Okay, first all this chemical energy to electrical work conversion device are not limited by Carnot efficiency, and this strategy is called cogeneration. Okay, so that not only you're generating electrical work, that high temperature steam is used for running a turbine, moving a piston. Okay, so that efficiency can be 90%. Right. So this is very, very important to understand. That's why people are interested in electrochemical devices, and typically two electrochemical devices, right? So you are aware of fuel cells and batteries. Okay, so in many ways, biological systems also use such processes. Okay, so that's something which I want you to understand.